that you're doing in the belly of a star might start to die down after making iron. So a lot of the very big stars have an iron core. And those stars that basically have a belly full of iron basically have turned all of their matter, all of the lighter elements, into iron by doing nuclear physics. So every star is basically a nuclear reactor. So imagine having a nuclear reactor in your belly. And as long as you're still doing some kind of nuclear physics, you're good. Your reactor still works. And you can make heavier and heavier elements. But generally, once you've made iron, you're starting to maybe die down a little bit because iron is very stable. And so to make the elements heavier than iron, you need more pressure, more heat, more energy. So once you start doing that, you're gonna burn out even faster, okay? So anyway, a lot of massive stars do have an iron core, meaning that they were able to make a ton of iron. And that becomes their core. If you have enough heat and energy and pressure to make iron, then why not? So anyways, once such a star collapses because it no longer does nuclear power and it no longer has an active nuclear reactor able to basically exert pressure outward to keep it as a star that's burning, it instead will collapse under its own gravitation because a star has a lot of mass and the gravitation wants it to collapse, wants it to get compressed down. Gravitation wants us all closer together, compressed, collapsed. We talk about this even in the scale of the universe as far as why the universe doesn't collapse on itself, right? So same thing goes for a star. Once it collapses, its collapse can be very extreme depending on the mass of the star. It can make something like a white dwarf if it's sort of a smaller star, like our sun. If it's something like our sun or maybe sun and a half mass, like 1.4-ish solar masses, then the endpoint will be a white dwarf, which is supported by electron degeneracy pressure. I'm still answering your first question, Austin, because you asked a good one. So I'm gonna keep answering that one. And then we'll move on to the next question. Okay. Can we get 10 likes? Can we get a super chat, by the way? That would be most helpful. So, depending on the mass, if it's something like 1.4 solar masses, it will become a white dwarf. And you might ask, why does it become a white dwarf? Why does it not collapse to a black hole, even when it's 1.5 solar masses? And that is because there is something else at play, keeping this object as a compressed object, but not so compressed that it becomes a black hole. And that thing is electron degeneracy pressure. So we talk about this too in a lot of detail in previous lives. You may want to check those out. The next thing is the stars that are even heavier than 1.5 solar masses. Those, when they die and they collapse, they become neutron stars. And that's another type of compact object where the gravitational collapse has led to a compression and a collapse down to a neutron star. And neutron stars have the radius of same size as Manhattan. So like a 10-mile radius. So that's not very big. That's very compressed. So when we first discovered neutron stars, to see that level of compression of a massive object, like a massive star, compressing down to the level of an object whose radius is the size of New York, was